Hello everybody. So today we're going to be talking about Fourier series, which is the last topic in Math 222 differential equations. So we're going to begin by doing a little mini review on Taylor series. So Taylor series is a way to write a function as an infinite sum of its derivatives. So fn of x naught n factorial x minus x naught to the n. And this is a Taylor series centered around x naught. So what does a Taylor series tell us? Well, we have a point. I'm just going to say x naught is 0 for now, but it can be anything. And we have an infinite amount of local information about this point. So if we just were to do in a little example, e to the x is equal to x to the n over n factorial, centered about the point 0. Hopefully this isn't a surprise. It's calculus 2. So 1 plus x squared over 2 plus dot, dot, dot. And what is this? So we have a little information about what the point is, so not even its derivative, but just the function at that point. It's 1. We have a little bit of information about the point right there. Its slope is 1. And if we were to draw it out, it's going to look something like that. And this tells us everything we want to know about as many derivatives as possible, restricted to this little domain. And that means that Taylor approximations are, and I used this word before, but they're really a local sort of series. So they only tell us everything we want to know about this tiny little area, which was great for some initial value problems because we knew information about the function at a point and we knew information about its derivatives at a point. But now we're moving on to boundary value problems. And boundary value problems are a bit different because now we're not really talking about the derivative, but we're talking about the value of a function at multiple points. So that's where Taylor series kind of fall flat, and there's two problems with Taylor series that we're going to find. One is we need our function to have a derivative, first off, which there are some functions that you've encountered in Math 222 that don't have derivatives. They're not differentiable at all points. And then we also need something that's not local, or we'll say, well, where we can work on an interval. So we want to say, how does a function behave at boundary value points? Because we have boundary value problems. So we need something different. And that something different is a Fourier series. So a Fourier series, as you could probably tell, was discovered by Fourier, and it really solves the problem that we were talking about before. So say I have a function on some symmetric interval, negative L to L, and in differential equations, sometimes you'll just say that L is pi, but I'm going to keep it general for now. Then we have some curve. And we want to represent this by an infinite series. But we don't know really anything about the derivatives, and we don't care. We just know about the function on this interval, the points on the boundary, and we feel that that should be sufficient to give us what we want. So, turns out it is. And we can actually write this function in a series of the following form. It's an infinite sum. And it's an infinite sum not of derivatives, but of cosines, and pi x over L, and sines, and pi x over L. So all of this, and what we're going to end up with, if we choose an appropriate set of ANs and BNs, we're going to end up with our function, our original function. Now, the question might be becoming, 1, how does this work? And 2, how do we find these coefficients? And that is what I'm going to prove for you. You also may see your professors write this, and I'm going to use this notation as also a0 over 2 plus the sum n equals 1 to infinity an cosine n pi x over L plus bn sine n pi x over L. And why this 2 appears, and then why we pull this out, I'm going to explain, and hopefully it's going to become apparent. So I'm going to just erase the board real quick, and then we will get back into it. All right. So to find these coefficients, these ANs, these BNs, and this A0 right here, we're going to need 3 integrals. We're going to need 3 integrals to help us find this. Technically, it's actually 5, maybe like 7 integrals, but there's only 3 unique ones. Let's use a different color. Let's choose this. And I'm going to prove one of them, and then the other one should be apparent how you do the same thing. So we're going to say, we're going to do this integral from negative L to L of sine of m pi x over L times sine of n pi x over L dx, where m and n are both integers, and integers are represented by this little z. So how do we do this integral? Well, if we go back, and this isn't really important for your test, but it's important to see where these forms come from and where the formulas that you'll eventually get the coefficients comes from. So we can just blast through this pretty quickly. We can use a trig identity, the product to sum formula, and we'll find that this integral is just the same as this one, which is 1/2 times the cosine of m minus n pi x over L minus cosine m plus n pi x over L dx. Now, there are 2 cases that we have to consider. There's the case when m is not equal to x, or n, and when m is, in fact, equal to n. So, very easily, if m is equal to n, then we find that this right here is equal to 0. And cosine of 0 is equal to 1. So that our integral then becomes 1/2 negative L to L of 1 dx plus, or minus, 1/2 integral negative L to L cosine m plus n pi x over L dx. And I kind of scrunched this up tight, but cosine is a periodic function over, this is an integer, so we're actually going to be doing it negative L to L over a full period. So this integral actually goes to 0. You can verify this yourself. A cosine integral, it's a very easy integral. I just don't want to write it out. And then this integral right here just becomes 1/2 times x at negative L to L, which is just equal to L. And then, that's if m is equal to n. And then if m is not equal to n, then this is not 0. But this is just instead some integer. And if we were just to apply the same process, this would not be 1. Right here, this would not be 1. But this would instead be some cosine of some m minus n pi x over L. And this whole integral would then go to 0. So we find that this integral right here has two things. Well, if m is not equal to n, then our integral, I'll write it out this way, then our integral is 0. But if m is equal to n, then our integral is actually just equal to L, where L, in case it would have been nice to have a picture, L is some symmetric domain that we're representing our Fourier series function on. So we have this integral, and we're going to need three others of a similar form, and I'm just going to take a second to erase it and write them all out, and then I'll explain. Okay, so this is where we're currently at. Let's just write the other integrals. Well, if we have one for sines, we should also have one for cosines. And you can actually prove this result the exact same way with a little change to the trig identity as I did before. And it's just 0 if m is not equal to n, and L if m is equal to n. And that shouldn't be too unbelievable because of the results that I showed here. Now, there's another one. What if we have a mix? So sine n pi x over L times cosine n pi x over L. And if you do the formula, you'll actually find that this is just always equal to 0. It doesn't matter if m and n are the same, it will always be 0. And then two more integrals, but these are easier, and they're just straight from Calculus 2. Sine of n pi x over L dx is 0, and cosine of n pi x over L dx is 0. So, these are all the integrals that we're going to need. I'm going to erase them, but you can write them down, pause the video, and copy them down. And while it's not very clear from here what the next step is going to be, it's interesting to see that all of these products and the original integrals, they're all 0 unless a very specific condition is met. And we're going to abuse that condition in order to find what our coefficients are. So, with that said, I'm going to erase the board and we're going to get into finding the coefficients. Okay, so now we have our integrals, so we're going to try to show how to get a particular coefficient. So we have our function that we want to represent. It's right over here. And we are representing it by this infinite series. And you might have noticed that I swapped out the n's for k's. And that might be apparent in a second, but I just wanted to change the lettering a little bit. So what we're going to do is we're going to take both sides of this equation and multiply by sine of n pi x over L, where this n is some n in particular. We're going to be choosing an n. Sine of n pi x over L. So we might be, say, multiplying by sine of 2 pi x over L or 3 pi x over L. But this is one particular number. It's not a series. So now we have this new equation where it's f of x sine n pi x over L for some particular n equal to a over 2. And I'm going to not write it out all the times, but I'm going to instead just say it distributes because it's multiplication. Cosine k pi x over L plus bk sine k pi x over L times sine n pi x over L. And note that this multiplication, it multiplies here times this one, and it also distributes into this sum. So we would have a1 cosine of, k pi x over L, I'm just going to put dots, times sine, or you know what, actually let me write it out. Because this is a1, so it's going to be 1 times pi x over L times sine n pi x over L plus b1 sine 1 pi x over L times sine of n pi x over L. And, it's an infinite summation, but this sine gets distributed, into this entirety right here. So what we're going to do is we're going to take both sides of this equation. Let me just erase to open up a little bit of room here. We're going to take both sides of this equation and integrate. So we're going to integrate from negative L to L of this whole thing, dx, and we're going to integrate this side of the equation from negative L to L, dx. Now, this sums out. And integrals, remember the integral of a sum is the sum of the integrals. So this right here is going to be equal to the integral from negative L to L of a0 over 2 sine n pi x over L plus the integral from negative L to L of a1 cosine 1 pi x over L sine n pi x over L plus dot dot dot. It's going to do this for all the b's and all the k's. And remember from our integral formulas, this is just sine from negative L to L, so this is 0. This is cosine times sine, so this one is 0. And then this is going to be 0 for every single integral except when k is equal to n. Because when k was not equal to n, and when we had the cosine times sine is all 0. And then we have the sine times sine. If k is not equal to n, then the integral just goes to 0. So then we end up with sine squared n pi x over L dx, which is, that's an integral that we just had. So writing it out, we can say the integral from negative L to L of f of x sine n pi x over L is equal to, oh, and I forgot there's an AK, right, or a BK. There's a BK factored out because there was the BK coefficient. I forgot to write it, my mistake. Is going to be equal to BK times the integral from negative L to L of sine n pi x over L times sine n pi x over L. And from our integral formula before, we actually know what this is. This is just L. So that's just equal to L times BK, which means we now get our first formula. So if we want to solve for BK, BK is equal to 1 over L times the integral from negative L to L of f of x sine n pi x over L. That is our first coefficient formula. It's a little bit of work, but there's the result, and that's how you get it. That's how you derive it. So I'm going to erase the board real quick, and then we're going to find our AKs, which is going to be the same process, super easy, and then we're going to find our A0s. So just give me 1 second. Okay, so as you can see, I actually left a lot of the board so I don't have to write. And also, I made a very minor error in the past section, and I wrote the formula for the B coefficients on this side, and I said it was BK was equal to this, when in fact it's actually not. It's Bn is equal to sine n pi x over L times the function. And that's because this is for a chosen n, and that's why we switched out from this being n to this being k. So we can choose a particular n and then find that particular n's coefficient. Sorry about that, my mistake. So let's do it for the cosine, and we're going to not mess up the k and the n's this time. So we're going to apply the exact same process, but I'm going to make one minor restriction. For now, we're going to say n is not equal to 0. And we're going to multiply both sides of this function by cosine of n pi x over L. So we're going to have the same thing, just changed up a little bit. And we're going to still integrate from negative L to L, dx both sides. And like we had before, all of these will go to 0 except the one case in which k is equal to n, and that will not be equal to 0. So what we have is from negative L to L of f of x cosine n pi x over L dx is equal to Bn times negative L to L of cosine n pi x over L times cosine n pi x over L dx, which, again, we know this is just L. So we get a very similar formula to say that this is not B, this is actually AN. My mistake, because cosines are A's. So AN, if we divide by L both sides, we find AN is equal to 1 over L times the integral of f of x cosine n pi x over L dx. And that's our AN formula. And as you can see, it's almost exactly the same as our Bn formula. The only difference is, instead of having sines, we have cosines. And that should make sense because we're not working with sines here, we're working with cosines. So it should be fairly obvious that the two of them would be different in that regard. I'm going to erase the board, and we're just going to find out what about this A0. Okay, so before we had cosine n pi x over L, and we multiplied. But now, instead of saying cosine is not equal to 0, let's say cosine, or n is equal to 0. And cosine of 0 is just equal to 1. So let's multiply both sides by 1 and do exactly what we were doing before. So we multiply both sides by 1. We integrate each side. This one does not go to 0, but all of these do, because all of these are just sines and cosines. So we then end up with a new integral, negative L to L of f of x times 1, which is just f of x, dx is equal to the integral of negative L to L times a0 over 2 dx. Now, we can do this integral. It's different. It's not one of our original forms, but we can still do it. It's an easy integral. A0 x over 2 from negative L to L, and that is equal to A0 over 2 L plus L, because it's minus of a minus, which is 2L, which is just equal to A0 times L. Right? Because before, the integral was just equal to L. But now, this range has 2L, which is where this over 2 comes from, because we need to cancel that out. So, taking that in, we get our final form. A0 is equal to 1 over L, negative L to L, of just the function itself. which is a little different. Now I'm going to take these formulas, I'm going to write them on the side, and we're going to work through one example. Okay, so we're going to do our first example, which, as you can see, I've changed the graph of f of x over here. And we're going to do it for our unit step function. It's a function that is 0 for all x less than 0, and as soon as x hits 0, it switches over to 1. This is a pretty easy function to do, so I think it's a good example. So let's first start by finding our a0 coefficient. So if we just use the formula, a0 is equal to negative pi to pi, because, didn't specify, but x is restricted to the domain negative pi to pi. So that's our L. We don't have it on any arbitrary L. Now we're just having it on this little interval. So what we're going to do is we're going to integrate our function. And our function is piecewise, so let's split this integral. And 1 over L is actually just 1 over pi times the integral from negative pi to 0 of 0, because that's what our function is, plus 1 from 0 to pi dx. This integral is just 0, and then this integral is going to be equal to 1 over pi times x evaluated from 0 to pi, which this whole thing, this right here is equal to pi. So pi times 1 over pi is just 1. So 1 is equal to a0. So pretty simple, pretty easy. Let's move on to one that's a little bit trickier. Let's do an, any an coefficient from negative pi to pi. So we get f of x times cosine n pi x over L dx. We're going to do this in the same way as this one, so every contribution from negative pi to 0 doesn't matter because f of x is 0 there, so we can actually just simplify this down further to 1 over pi from 0 to pi, and then it's 1, so cosine n pi x over L dx. This is a very easy integral. Just switch it. So that's equal to negative 1 over pi times, oops, my mistake. This L is pi, so actually this makes this integral even easier. I'm so used to fully writing it out that when I can simplify it down, just to say what my mistake was, L is equal to pi. So n pi x over L is just equal to nx. So that's cosine of nx. So if we're taking this integral cosine nx dx, that's equal to 1 over pi times negative 1 over pi times 1 over n sine of nx from 0 to pi. And that should be what I got. Yep, that's correct. Now, look at this. This is equal to negative 1 over n pi right here, if we factor that out. But this is sine of pi x minus sine of 0, which is always just equal to 0. So it doesn't matter what our n is. Our an coefficient is just always equal to 0. So this is nice. We've actually just cut out a very large section of all possible coefficients we could have. So I'm going to erase real quick, and then we're going to get into the BNs, because BNs do not do this. So it's going to be a little more work. So we've found our A0 and our ANs. Now it's time to find our BNs. Bn is equal to negative L to L, and I'm actually not even going to write out the L's. I'm just going to put it all in forms of pi. 1 over pi, negative pi to pi of f of x times sine of n pi x over L, which is just sine of nx dx. Again, if we split this integral in half, we get from 0 to pi of f of x, which is just 1, sine nx dx. And just like before, this is an easy integral. So we get 1 over, and this is going to be negative 1 over pi. In my past example, I put a negative sign when I actually probably shouldn't have, but it didn't matter, it all canceled out to 0. 1 over n cosine of nx evaluated from 0 to pi. Now before, in our past example, sine at 0 and pi is just 0. So the entire solution, regardless of these coefficients, just became 0. And that was the correct answer. But cosine is not. So if we just expand this, negative 1 over n pi, pulling out the n, times cosine of n pi, plugging in into x, minus cosine of 0, which is just 1. And that's our Bn coefficient. But we can actually further simplify this down. So look at this term right here. Cosine of n pi. Well, what happens? N is always changing. N is equal to 1, 2, 3, off to infinity. So what happens when cosine of n, when n is 1? Well, that's cosine of pi, which is equal to negative 1. And then when n is 2, we get cosine of 2 pi, which is 1. And then cosine of 3 pi is equal to negative 1 again. And cosine of 4 pi is equal to 1. And the pattern will repeat, and it will alternate. It will go from negative 1 to 1, and negative 1 to 1. And only on the odd numbers, the odd ends, will it be negative 1, and on the even ends, it will be positive 1. So that's almost as if we can just say cosine of n pi is equal to negative 1 to the power of n, right? And it's kind of weird to switch from a cosine to a negative 1 because this is almost discrete and this is continuous, but we're just changing the n, and n are only integers. So cosine of 1 pi is negative 1, negative 1 to the 1 is negative 1, and the pattern holds true. So we can take this and we can plug this into here, negative 1 over n pi times negative 1 to the power of n minus 1. And that's our Bn. But we could even simplify this more. So if you take this on any odd term, so when n is equal to 1, 3, 5, off to infinity, this is negative 1. So we get that this whole quantity is negative 1 over n pi times negative 1 minus 1, which is equal to just 2 over n pi. But when n is even, 2, 4, 6, off to infinity, we get that this is equal to negative 1 over n pi times 1 minus 1, which is actually equal to 0. So whenever n is even, our BK coefficients are just 0. And then whenever n is odd, our BK coefficients are this. So we even have only half of the BKs that we wanted to get. Or our BNs. Sorry, I keep using K when actually it's n. Our BN coefficients are this, and our BN coefficients when n is even is 0. So if we were to write this out, you can write it out in a bunch of ways. I always like to use Bn is equal to 2 over n pi, either n equal to 1, 2, or 1, 3, 5, dot, 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 or n is odd. Or if you want to graph this, and you want to have n equal to 1, 2, 3, because you can't skip numbers, you can actually convert this into only odd numbers by saying 2 over 2 times n minus 1 times pi, and this will give you only odd numbers, skipping all the even numbers. But I think it's a little less elegant, so I'm going to write it out this way. Both ways should be acceptable on a test. So let me just clear the board off, and we're going to put it all into one final Fourier series. All right, so now we have all of our coefficients, so we're good to go. We can write this out. F of x is, I'm going to do a little tilde because it's technically not equal to, it's modeled by, but it's details. Then we're going to do our a0 over 2 coefficient first, so we get 1/2 plus our infinite sum of n equals 1, 3, 5, only the odd numbers because that's all we have for our Bn coefficients, and all of our Ans are 0, so it's only the Bn's, and it's 2 over n pi sine n pi over L, where L is n, so of nx. And that's our answer. That is the Fourier series for this step function, and you might be wondering why I didn't write an exact equal sign when I have been. And it's because if we just plot out this Fourier series real quick, just to finish this up, and we do pi, 2 pi, 3 pi, negative pi, negative 2 pi, negative 3 pi. On our interval from negative pi to pi, if we were to sum this up an infinite amount of times, which we can't, but we'll just say we can for now, we would get back our step function, and it's exactly equal. But because sine is periodic, let's just plot some of these terms. Here's our a0, our 1/2. And then if we plot our first one, which is sine, it's going to look like that. Sine of 1x, it's going to look like this. And then if we plot our next term, it's going to look like this. Like this. So the entire thing is periodic. We're not just restricted to this domain right here that we said was our L. So in fact, if we were to just, I'm going to make a new little separate, smaller graph. if we were to add all these up infinite amount of times, we would actually see that our step function was repeating itself. And it would look like this, where these are, this is 2 pi, this is 3 pi, negative 2 pi, negative pi, pi. So we don't just get our function on this interval, which is why I wrote this. It's not equal to the function outside the interval. Instead, it's a little bit different. It's turning our function into a periodic form, which is what we call the periodic extension. You'll hear that a lot. And this will happen for every function. And you can do it for, this only has sines, so this is a Fourier sine series, and you can get all sorts of different series and all sorts of different periodic extensions. But that's all we have time for today. So I'll leave you with that. There's a bunch more examples you can do. Just take literally any function you want, and you can come up with a Fourier series for it, plug it into Desmos, and graph it. It looks very cool. So with that, I'd like to thank the Institute for Teaching Excellence for letting us use this whiteboard. It's really phenomenal. And I would also like to say, if you'd like to join Math Club, just send an email to me, wjm9@njit.edu, and say that you are interested in Math Club, because we do cool stuff like this. All right, that's it. Thank you very much.